Welcome to the first video of 7 Steps to a 7 in Olympiad Algebra. This course will cover the most fundamental concepts in Olympiad Algebra. We're going to be starting off by reviewing some things that you probably know already, for example, polynomials and symmetric sums. And then we're going to build up to common topics that you'll see, like functional equations, and then briefly touch on some less frequent ideas such as polynomials and inequalities. But before we get started, I want to give a quick warning and say that this course is not intended to be comprehensive. And sure, this course technically covers most of the theory you may need to know, but in reality, you need to much more practice in order to solve the harder problems you come across. For example, there are some incredibly hard functional equations that are problem 3 level, and we're going to be only focusing on the ones that are problem 1 level and sometimes problem 2 level here. I'm only going to go over the basics here and bridge the gap between concepts on short answer tests like the AMY to introductory ones that you may find on Olympiad. That way, it won't be like you don't know what to do when you come across an Olympiad algebra problem. And yes, I'm assuming that you're reasonably comfortable with qualifying for your country's national Olympiad. And for those of you in the US, this is equivalent to around a 6 on the AMY. If you don't have any of these qualifications, then that's completely fine. Don't get me wrong. But I want to make sure that you aren't learning material that is too hard for you to begin with. From personal experience, if you do, then you'll come out of this course more confused than when you first started. So you should start learning the material when you are ready to learn it. Please do not get too ahead of yourself. All right, I've said enough. Let's go ahead and get started with our course. So before we get started with the theory and everything, I want to go ahead and tell you guys a secret. And it is that Olympiad Algebra is all about computations and manipulations. This is literally it. Just computations and manipulations. And this is partly the reason why most people might tell you that Olympiad Algebra is quote unquote dead. But the reason why we have Olympiad Algebra as its entirely own subject is because these computations and manipulations disguise themselves in very interesting ways. For example, it could be in the form of a functional equation like f of x f of y plus a f of xy is equal to f of xy here. And it could also be in the form of an inequality, for example, this one here, a cubed plus 3b cubed over, I think it's 5a plus b, then plus b cubed plus 3c cubed over 5b plus c, plus c cubed plus 3a cubed over 5c plus a is greater than or equal to 2/3 of a squared plus b squared plus c squared. Anyways, the point is that these computations and manipulations can always disguise themselves in these forms. And what I want to do in this series is go over all of the most common ways these computations and manipulations hide themselves in the problems. For example, it could be in inequalities or functional equations. But throughout the course, I'll be emphasizing these manipulations and computation inside algebra. Because really, the only way to get better at this, because there's no way to get better, the closest you can get to a magic way of getting better at computations and manipulation is practice. And practice is what makes perfect in this case. Even some of the best Olympians that you may know don't have this entirely mastered. And what sets them apart from others is that they have seen so many different of these Olympiad algebra problems that they know what exactly to do and what to expect when they see a new one. And what I want this course to do is provide lots of practice problems and lots of tricks in how these computations and manipulations disguise themselves to help you enhance your intuition. So without further ado, let's get started. We're going to be starting off with polynomials and symmetric sums. And raw problems involving symmetric sums rarely ever appear on Olympiads, but I'm dedicating this video to them because they're one of the key building blocks of Olympiad algebra. So without further ado, let's get right into it. So we're going to go ahead and get this ball rolling by discussing polynomials and reviewing them. So what is so special about polynomials that we need to know? Well, most of the facts about polynomials in Olympiad algebra come from the following few facts. So suppose that like p of x is our polynomial, and we know that p of r is equal to 0. And I forgot to say that p has its coefficients inside the complex numbers. So what we do is say that p is inside cx here, where this is a complex numbers. This means that p has its coefficients in the complex numbers. Anyhow, if p of r equals 0 for a complex number r, then we say that x minus r divides p of x. We know that this is true. And this is called the factor theorem. And there's a very related fact, and it is that p of x, if it has degree n, meaning that's the highest coefficient of it, then it has exactly n roots which are complex. And they're counted with multiplicity. So we can always find complex numbers r1, r2, all the way to rn, which are not necessarily distinct, such that p of x is equal to ax minus r1, x minus r2, so on and so forth, to x minus rn. And this fact here, that every single polynomial can be factored like this, is known as the fundamental theorem of algebra. And this is way more powerful than you think, because we can end up going between the roots to the polynomial itself. And if we have a bunch of roots, then we can determine the polynomial. We can also go back and forth between the roots and the polynomial itself. So suppose that we have that p of x is equal to our polynomial, and it's an x to the n plus a n minus 1 x to the n minus 1 plus all the way to plus a1x plus a0. So these are the coefficients. And suppose that it has roots r1, r2, all the way to rn, as guaranteed by the fundamental theorem of algebra. Then what Vietta's formulas tell us, so I'm going to go ahead and say Vietta, is that the kth elementary symmetric sum is equal to negative 1 to the k, a n minus k, over a n. Now, what exactly is the kth elementary symmetric polynomial? We're going to be talking about this a bit later in this video, but the first one, for example, is just the sum of the roots, r1 plus r2 plus so on and so forth, plus rn. Then the second one is r1, r2 plus r1, r3 plus all the way to plus, and we're going over all pairs of these. So basically what the kth elementary symmetric polynomial is that it takes all bundles of k of the numbers from 1 through n, and it puts them under r. So we have r1, r2, that's one choice, because 1, 2. We could also have like 3, 5, and that gives r3, r5. And note that we never count a pair or bundle twice, because we have 3, 5 is not counted if 5, 3 is counted. Anyhow, this is the elementary symmetric polynomial, and what Vietta's formulas tells us is that it is equal to this. And some particularly useful ones is that r1 plus r2 plus all the way to plus rn is equal to negative 1 to the k a n minus 1, or this should be, we don't even need the negative k, so negative a n minus 1 over a n. And then r1, r2 all the way to rn, which is the product, is negative 1 to the n, a0 over an. So this is basically Vietta's formulas. Now we have a slightly less useful consequence of the fundamental theorem of algebra and the factor theorem. And it is that if p and q both have degree at most n, so degree p and degree q have degree both less than or equal to n, if p of x equals q of x for n plus 1 distinct values of x, then that means that p of x equals q of x for all x. And this is a case because, for example, the polynomial p of x minus q of x has n plus 1 roots. And so by the factor theorem, it must be the product of x minus something for n plus 1 of those. And that will make the degree greater than n unless it's 0. So this is basically the fact called interpolation. And we're going to be discussing some more general cases of interpolation later, but this is the main thing you need to know. And finally, we have a generalization of the factor theorem for multivariable polynomials, which will be useful when we look at symmetric sums later in this video. So suppose we have a multivariable polynomial expression, px1, x2, all the way to xn. And this is in multiple variables, so it could be something like the product of all of them. It could be like x1 plus x2 squared plus x3 cubed plus so on and so forth. It's just a multivariable one. If we have p of x1, x1, x3, all the way to xn as a polynomial is equal to 0, so it is 0 for all of these inputs here, then this implies that the polynomial x1 minus x2 divides p of x1, x2, all the way to xn. Now this is very, very useful when we want to factor multivariable polynomials. So to make sure that we're on the same page, let's go ahead and take a look at a quick example of all of these playing together. Let p be a degree 3 polynomial such that p of 1 equals 1, p of 2 equals 4, p of 3 equals 9, and p of 6 equals 7. What is the value of p of 5? Now, the first thing that strikes out to us is that 1, 4, and 9 are the first 3 perfect squares. So in particular, we know that p of 1 is equal to 1 squared, p of 2 is equal to 2 squared, p of 3 is equal to 3 squared. And we have this value of p of 6 over here that we want to somehow use later. Okay, so what do we do with this information here? Well, one thing I want to emphasize here is that if we know that p of x equals x squared, for one other value of x, then we know that p of x must be identically x squared. But then that's not the case because of this one here. So we know that there's a bit of other stuff involved. We want to see how close we are to p of x being x squared. So let's go ahead and subtract x squared from p of x. Then we know that p of x minus x squared, p of 1 minus 1 squared is 0, so that means that this polynomial has 1 as a root. So if we have a leading coefficient a, then it is x minus 1, similarly x minus 2, x minus 3. And therefore p of x is equal to a x minus 1, x minus 2, x minus 3, plus x squared. And we know it must be of this form, where a is some complex number. And now we can finally use this information to our advantage over here. And we get p of 6 is equal to a times 5 times 4 times 3 plus 36 is 7. So 120a plus 36 equals 7. So a is equal to negative 29 over 120. And thus p of x is negative 29 over 120, x minus 1, x minus 2, x minus 3, plus x squared. And notice how we solve for p of x here. By using the fact that p of x minus x squared has 1, 2, and 3 as its roots, and then using the factor theorem to our advantage. Anyhow, we now have this as a case, and we can just plug in 5 into this. So p of 5 is negative 29 over 120 times 4 times 3 times 2 plus 25, which is 25 minus 29 over 5. And this comes out to, I think, should be 96/5. Now let's talk about some ways we can manipulate these symmetric sums. So Vieta's formulas allows us to compute R1 plus R2 plus R all the way to plus Rn, and also R1, R2 plus R1, R3 plus all the way to plus Rn minus 1, Rn, and so on and so forth. But what if we want to compute something like R1 squared plus R2 squared plus all the way to plus Rn squared? This is not in our list over here. And the solution to that is we actually have the following identity. The sum of squares here is R1 plus R2 plus all the way to plus Rn squared minus 2 times R1 R2 plus R1 R3 plus so on and so forth plus Rn minus 1 Rn. So in other words, we have the symmetric sum over here, and we ended up getting it in terms of these symmetric polynomials, the elementary ones, as we got here. And is it always possible to do this? Well, yes, it is. But we first have to know exactly what a symmetric sum really is. Because after all, if we don't have something that's like not really symmetric, then we can't really do what we want to do. So what is a symmetric sum? So suppose we have n variables x1, x2, all the way to xn. And we have an expression in terms of them. And we say that it is symmetric if like switching any two doesn't really change the expression. So switching any two here, and because we can end up switching any two we like at all, we end up getting that if we permute these variables here, so let's go ahead and call our expression p, then p of x1, x2, all the way to xn is equal to p of x sigma 1, x sigma 2, all the way to x sigma n, where this is a permutation. And we have that this is the case here. And that is what it means for an expression to be symmetric. And as I said earlier, it's always possible to express the symmetric sums in terms of the symmetric polynomials. So for example, as I said earlier, we have that the sum of xi squared is equal to the sum of xi all squared minus the sum of xi xj, where this is like s2 and this is s1. And we also have some more complicated things. For example, sum of xi squared xj, where we have that one here, is in fact equal to, I think it's s1 s2 minus 3s3. So this is like x1 plus all the way to plus xn, then x1 x2 plus x1 x3 plus so on and so forth, minus 3 times x1 x2 x3 plus x1 x2 x4 plus so on and so forth. So the point that I want to make here is that it's always possible to do this, and you just need to figure out how. And in fact, figuring out how is pretty studied in a very special case. So suppose we have our symmetric sums, so s1 is equal to x1 plus all the way to plus xn, s2 is equal to x1 x2 plus so on and so forth, and so on and so forth. Sn is equal to x1 x2 all the way to xn, and then Sn plus 1 is equal to 0. Sn plus 2 is equal to 0, so on and so forth. Then suppose that we instead define p1 is equal to x1 to the 1 plus x2 to the 1 and xn to the 1. P of 2 is equal to x1 squared plus x2 squared plus all the way to plus xn squared. Then Pn is equal to x1 to the n plus x2 to the n plus so on and so forth plus xn to the n. So we just have the sum of the nth powers of these roots. Then how do we compute the pi in terms of the si? Well, as it turns out, we have a very special recurrence. So we have P1 is equal to S1, well duh. Then we have P2 is equal to S1 P1 minus 2S2. Then P3 is equal to S1 P2 minus S2 P1 plus 3S3. P4 is equal to S1 P3 minus S2 P2 plus S3 P1 minus 4S4. And we just keep going and going. And this is known as Newton sums. And in this way, we can end up computing all the PI. And Newton sums are not super common because these are more computational tools than anything. But the thing I wanted to demonstrate with this is that it is always possible to express a symmetric sum in terms of the elementary ones provided here. Now, before we go on to the examples, I want to go ahead and go through some very common identities that you'll find in Olympiad algebra and even beyond that. So one of them that we discussed earlier is that P2 is equal to S1 squared minus S2. And we also have P3 minus 3S3 is equal to P1, or it's going to be S1 times S1 squared minus 3S2. And both of these follow from Newton sums. And this is also equal to P1 minus S2. And yeah, both of them follow from Newton sums. And we have some more useful 3-variable ones. For example, these ones here can be written in 3 variables. A plus B plus C squared minus 2AB plus BC plus CA is equal to A squared plus B squared plus C squared. And then A cubed plus B cubed plus C cubed minus 3ABC is equal to A plus B plus C times A squared plus B squared plus C squared minus AB minus BC minus CA. So we have this over here. And we have some more useful 3-variable identities. For example, we have x squared y plus xy squared, or I should write this as y squared x, plus y squared z plus z squared y, plus z squared x plus x squared z, plus 2xyz is equal to x plus y, y plus z, z plus x. And then if you end up replacing this with plus 3, well, you also get that as factorable. So x plus y plus 3, x plus y plus z, and then xy plus yz plus zx. And what if you have the x cubed plus y cubed plus z cubed here? Then you have x cubed plus y cubed plus z cubed. Well, then it again factors, because then it's x plus y plus z, x squared plus y squared plus z squared. And we can tie a bunch of them together by doing x plus y plus times y plus z times z plus x plus xyz is equal to x plus y plus z times xy plus yz plus zx. So these are some very useful identities. And the thing I want to stress is that you're going to learn so many more identities as you do more Olympiad math. These are just the most common ones, but the more algebra you do, the wiser you'll become and the more identities you'll know. And there's one more thing I want to cover. And suppose we have a monic polynomial P of t, meaning it has leading coefficient 1 and has roots x, y, and z. And we want to find P of x plus y plus z. How do we exactly do this? Well, for one, we could just plug into the equation for P of x. So we end up getting so we know P of x or P of t is equal to t cubed minus at squared plus bt minus c. and this one is here is equal to a. Then P of a is equal to a cubed minus a cubed plus ab minus c, which is ab minus c. But there's another way to calculate it, and it is by using the fact that P of x plus y plus z is equal to x plus y plus z minus x plus y plus z minus y, x plus y plus z minus z. Now, why exactly does this happen? And it's because P of t is equal to t minus x, t minus y, t minus z by the fundamental theorem of algebra. And oftentimes this can make the computation much, much, much easier. So now let's go ahead and try out the following problem from the 2014 USA Math Olympiad. And here's that it is. Let a, b, c, and d be real numbers such that b minus d is greater than or equal to 5, and all zeros x1, x2, x3, and x4 with multiplicity of the polynomial p of x equals x to the fourth plus ax cubed plus bx squared plus cx plus d are real. Find the smallest value the product x1 squared plus 1 and so on and so forth can take. So what I want you to do now is go ahead and pause the video and try out the problem on your own. And when you're ready to discuss with me, hit the play button. Okay, so hopefully you've tried out the problem by now. So let's go ahead and discuss it together. So one way we could try doing it is just by expanding this entire thing out and figuring it out in terms of the symmetric sums we all know and love. For example, we have x1 squared times x2 squared times x3 squared times x4 squared is just equal to d squared by Vieta's formulas. But the other ones aren't going to come as easy. So we really want an easier way. And with this in mind, recall that with our polynomial trick that I discussed earlier, we know how to find a minus x1, a minus x, or I should not use a again, but we know how to find like k minus x1, k minus x2, all the way to k minus x4, k minus x3. We know how to find this because it is just p of k. And we want to somehow use this. But the problem is we have an x1 squared plus 1. So we need to somehow split this. Now, if we have like x1 squared minus 1, x2 squared minus 1, so on and so forth, then this isn't particularly hard. Because it's then like 1 minus x1 squared, or I should not do that right now, but it's equal to x1 minus 1, x1 plus 1, and x2 minus 1, x2 plus 1, so on and so forth. And then this is like negative, this is like 1 minus x1, 1 minus x2, 1 minus x3, 1 minus x4, times negative 1 minus x1, negative 1 minus x2, all the way to, or I should also include negative 1 minus x3, and negative 1 minus x4. And this is p of 1 times p of negative 1. Now we want to find a similar factorization, but this time for x1 squared plus 1 instead of x1 squared minus 1. And then that's when we realize that we can just use the factorization x1 plus I, where I is the imaginary number square root of negative 1, then x1 minus I. Then if we repeat this entire process over here, we end up getting I minus x1, I minus x2, I minus x3, I minus x4, and then negative I minus x1, negative I minus x2, negative I minus x3, negative I minus x4. And therefore, the product we want to find is actually equal to p of I times p of negative I. Now we need to find out what p of I is in the first place. But thankfully, with this expression here, for p of x, we can just find p of I. So p of I is equal to 1, I to the fourth is equal to 1, then plus ax cubed, so that's minus ai, because I cubed is negative I. Then plus b squared, so that's going to be minus b because I squared is negative 1. Then plus ci plus d. So this is like d minus b plus, or d minus b plus 1 plus c minus a I. And we similarly have that p of negative I is equal to d minus b plus 1 minus c minus a I, if you do all the work. And therefore, their product is equal to the product of these two. And because it is the product of a complex number and the conjugate, we end up getting d minus b plus 1 squared plus a minus c squared. Now, this really involves our b minus d over here, so we're definitely on the right track. But we need to somehow make this d minus b instead. And when we do that, we end up getting b minus d minus 1 squared plus c minus a squared. Now, we know that b minus d is at least equal to 5. So this means that this term here is at least equal to 4 squared, which is 16. And this term here, what do we know it's at least equal to? Well, for example, if c equals a, then it's equal to 0. But otherwise, because the square of a number is always at least equal to 0, this is at least 16 plus 0, and that gives our answer 16. And we are done. Or are we? We still need to check that 16 is actually possible. And the way we do that is we need to construct a polynomial that has its value here equal to 16, but also has all of its roots real, and b minus d is at least 5. So let's go ahead and do this. So b minus d must be equal to 5, because that's the only way equality can hold in our sum of squares thing. And we also have c equals a. So that means that p of x is equal to x to the 4th plus ax cubed plus, then this should be d plus 5 x squared plus ax squared plus d. And this has all real roots. Now, it would be really helpful if all the roots are the same. And if all the roots are the same, then we know that it's like x plus r to the 4th, which is equal to x to the 4th plus 4rx cubed plus 6r squared x squared plus so on and so forth. And the point is that if all the roots are equal, actually, then if we want this to be 16, then we'd want each of these to be 2, or x1 equals 1. So that means that the x minus 1 to the 4th should do the trick. And indeed, we end up getting x to the 4th minus 4x cubed plus 6x squared minus 4x plus 1. And indeed, 6 minus 1 is equal to 5, and negative 4 is negative 4. And therefore, this ends up satisfying our condition, and therefore the minimum is actually equal to 16. Now, this last part of the problem is not the most important part of it. In fact, the thing I want you to take away from this problem is how we even computed this product in the first place. Because computing this product is actually the entirety of the problem, if you think about it. Because you end up using the imaginary unit to your advantage, and then plugging the imaginary unit in here, and we get an expression in terms of b minus d and c minus a, which is very, very, very easy to handle. Okay, so thank you so much for watching this video, and I'll see you guys in the next one where we start to look at some Olympiad inequalities.